your screen now.
Thank you.
Okay, whenever you're ready.
Okay, thanks. So good afternoon. My name is Zuzana Bardachova, and I would like to present our work which deals with the selection techniques for neutrino-induced cascades in Baikal-GVD neutrino telescope. Okay, so one of the main goals of the Baikal-GVD is to detect high energy astrophysical neutrinos. And this detector is located in the southern part of Lake Baikal, 3.6 kilometers from the shore. It is deployed at a depth of 1.3 kilometers. And Lake Baikal was chosen for deployment of the detector due to its high water transparency, lower radioactivity and bioluminescence. And moreover, the beneficial property of this lake is that it freezes from February to April. So thick ice layer allows the construction of the detector without using ships. Detector Baikal-GVD is a three-dimensional grid of the optical modules which are attached to the vertical cables called strings. And the whole detector is subdivided into functionally independent units which are called clusters. And on the right, we can see the situation from this year, 2022, where we have 10 fully operated clusters. Okay, the illustration of the cluster can be seen on the right. Each cluster is composed of 288 optical modules distributed over 8 strings. And so together for 10 clusters, we have 2,880 optical modules. And the photo of the optical module is on the left, attached to the string. Okay, as we know, in the neutrino telescopes, neutrinos are detected via secondary charged particles, which are produced in charge current neutral current interactions that cause the emission of the Cherenkov light. And according to this Cherenkov light shape, we can distinguish between different types of events. Two main event topologies are tracks and cascades. On the left, we can see the Cherenkov light cone, which is induced by muon from the muon-neutrino charge current interaction. And on the right, we have an early point-like source of Cherenkov light, which is called cascade. And this work is focused on this type of events. Okay. But however, the same light signature of cascades can be produced along muon tracks that originate from discrete stochastic energy losses, for example, Bremsstrahlung or photonuclear processes. And the illustration of such background cascades, which are produced along muon track, are on the left. Along one track, we can have several background cascades, and also we can see on the plot, in the plot on the right, the distribution of the zenith angle, of the reconstructed zenith angle, where we have on the horizontal axis, we have the reconstructed zenith angle from 0 up to 90 degrees, we have upgoing events, and from 90 to 180, we have downgoing events. Black dots correspond to the experimental data from part of the season 2019 for cluster 1, and the green line is for the Monte Carlo simulation of background cascades from atmospheric muons. And we can see that the most of the reconstructed data or cascades in the experimental data comes from the background cascades from atmospheric muon bundles, because these two curves are in good agreement, especially in this downgoing region. And this upgoing region for background cascades from atmospheric muon bundles are due to mis-reconstruction of the zenith angle. And several orders down in event rates, we have the neutrino signal cascades, which are produced by atmospheric or astrophysical neutrinos. And for that reason, it is essential to suppress these background cascades. And therefore, we try to develop some selection techniques which would better characterize signal and background cascades and improve separation between them. Sorry. So far, selection techniques were optimized with Monte Carlo simulated for season 2019, and therefore I will show results only for this year. So the first technique which was developed is called N-track heats, and this method is supposed to find out if the track is present in the event, which is the case for the background cascade. And the result of this method is the number of track hits present in the event. So, for example, in the middle in the picture, we can see on the horizontal axis we have the times of the hit times of detected hits, and on the vertical axis we have the Z coordinate of the optical modules which detected the hits, and different colors corresponds to different origins of hits. For example, here we have the small red point, which corresponds to reconstructed cascade time and Z coordinate. And then we have blue points, which are always detected earlier than the cascade hits, which are shown by black, because the muon has greater velocity than the speed of light in water. So we can see that the black points corresponds to cascade, and they lies in this green band, which is the expected theoretical expected time for cascade hits, and this orange line corresponds to the theoretical expected time for track hits, and this is the case for Monte Carlo background cascade. So the result of this method is shown in this right figure, where the number of track hits found by this technique is displayed. For the signal cascades, it is in by blue histogram, and for background cascades, it is shown by red histogram. We can see that the experimental data again are in good agreement with the background cascades, and in background cascades we have much more found track hits than in signal cascades, and some of the hits were like misidentified as track hits in this method, because in neutrino cascades we don't have any track hits like in reality. Okay, the next method which have been developed is called the branch ratio. The main purpose of this method is to count the number of hit optical modules which are located above the cascade, above the reconstructed cascade, and to count the number of hit optical modules below the cascade, and then to calculate the ratio of these two numbers. And so we suppose that for downgoing background cascades, this branch ratio variable should obtain lower values than for upgoing neutrino cascades, where the number of optical modules which are hit above the cascade is higher than below the cascade. So again, this variable also allows us to separate between signal and background cascades to some extent. Okay, after that, we used another technique which has been inspired by Antares collaboration. It is called the Q-early technique. It also tries to discriminate between background and signal cascades, but now based on the ratio of hits charges, especially total charge of track hits is divided by total charge of cascade hits. And so again, distribution is shown of this variable, of this Q-early variable is shown on the in the right plot. And again, we can to some extent separate between signal and background. After that, we used another, like two more variables, especially reconstructed zenith angle and chi-square value after cascade position reconstruction. And like to take the most of the discriminating power of all these variables, like 5 variables, 3 above mentioned and these 2. We used the multivariate analysis, especially boosted decision trees, which is implemented in the root. And so we trained and tested these boosted decision trees only for upgoing events, because we wanted to find some interesting event in the cascade channel. And here we have the result of the boosted decision trees training and testing. In the left plot, we can see the output value for the boosted decision trees, where the red histogram corresponds to background cascades and the blue one to signal cascades. And this distribution allows us to set some cut on the BDT value and to suppress background. So we, according to maximal significance, we set the cut on the BDT value, and we strongly suppress background and obtain a 50% signal efficiency. After that, the same procedure was applied on the experimental data for season 2019, and we applied the same cut on the BDT value, and also we wanted to find some interesting high energy events. So we applied cut to have reconstructed energy more than 50 TeV. And one interesting event was found in the cluster 1 with energy 80 TeV. The boosted decision tree value was quite high, 0.6. And this event was reconstructed as upgoing, as can be seen in this picture. And the above mentioned method, selection technique and track hits, found only one track hits in this event. Okay, and also we plot the dependence of the Z coordinate of heat optical modules on the heat detection times, where the again black dots corresponds to the experimentally detected heats for this upgoing event, and the green band corresponds to this like expected time where the heat should occur on a given optical modules. So we can see that for one cluster we had eight strings, and this experimentally detected heats lies in these green time regions. So, but it is not the final result. There should be done like a more sophisticated analysis about this event, but there can be some indication that this event can potentially be can be produced by neutrino interaction. Okay, so as this brings me to the conclusion that we developed some selection techniques to distinguish between signal and background, and then we used boosted decision trees and then applied it to experimental data, and found one interesting event which could potentially come from the neutrino interaction. Okay, so thank you for your attention.